Okay, welcome everybody to this keynote presentation, this afternoon keynote presentation. This is the fourth keynote of the conference of the International Micro Air Vehicle Conference. And I'm very excited to introduce our keynote presenter, Brandon Gilles. I will read his biography. Brandon is driven by the singular belief that the biggest impact he can have on the world is fostering innovation, and the understanding that a five-fold increase in productivity is the difference between the Middle Ages and now. And the driver of that productivity increase and the tremendous increase in the quality of life we all have is innovation. And for innovation to happen, simplification needs to happen first, so that powerful things can be used easily and readily. And then combined with other powerful things, of course, combined with other powerful things. So Brandon's mission is to make embedding performant spatial AI and CV, computer vision into products quite simple. To enable and foster a wave of innovation powered by being able to embed human-like perception into products across all sorts of industries. I have to say that Brandon is the CEO of Luxonics, a company that is offering very nice products in terms of sensing and novel cameras or novel sensing cameras. I'm pretty sure he will do a better job in describing what his company is offering, but I have to take the opportunity to also say thank you to Brandon, because on behalf of his company, he offered us a sponsorship for our awards, the awards that we are going to present tomorrow in the awards ceremony. So please, Brandon, you have the stage. And go ahead. Thank you.
Well, thank you for that great introduction. So, you know, the thing that I want to cover today is spatial AI and embedded systems. So to give you a background on all of those things. So the spatial aspect is depth sensing using two cameras, just like our eyes, to get depth maps of the world. And then the AI part is, mimicking the intelligence or the, more specifically, the perception that humans have. So this is computer vision, artificial intelligence, which is knowing what things are, what's in a scene, where they are, where they stop and where they end. And so both of these kind of started in the 1980s. So if you look at, spatial perception, this started in the 80s with PhD work, theorizing what's possible of being able to get depth information out of multi-camera arrays and like $100,000 plus or $1 million plus pieces of hardware that took tremendous amounts of power and still didn't really run real time. And AI started in the 80s too, with Geoffrey Hinton theorizing with backpropagation that you could get a computer to learn. And if you did that, then you could have computers solve problems that humans couldn't. And so if you fast forward to, let's say, 2012, we kind of had the first time that AI could really do that, where backpropagation was used at scale to outperform or to match human capability to recognize objects, to do image classification. And if you fast forward again to about 2012, you see depth perception start to be commonplace with companies like Occipital, for example, which started to push the boundaries where they got depth perception into the hands of consumers at, let's say, $500. I don't remember exactly what the price was. And in these systems, that was the first time they were kind of readily available to the masses. And so with AI itself, you saw all these huge applications take off. But they were in 2012 era, they were like infinite compute applications. So like Google scale compute and these startups that were, using millions of watts of power to do artificial intelligence. And then with depth perception, I was finally starting to get to the point where consumers could use it, $500. And since then, we've seen this kind of slow trajectory over those years into like more edge, right? And slow being a relative term, right? Like about a decade. But there's quite remarkable when you look at like the course of human history of what we're accomplishing here. And maybe starting in 2017, that's where you saw AI kind of get to the edge, right? So the edge being like a couple MacBooks, something like that. And then you started to see combinations of this where you do object detection, machine learning based object detection, YOLO, for example, with depth sensors, say like Occipital's depth sensor. And then you could make robotic systems that could interact with the world, but you're still talking about compute payloads that are the size of a couple MacBook Pros, right? And in 2017, it was remarkable to see a laptop. That was like the big deal. Like a laptop can run a real-time object detector, a machine learning based object detector, and then you could fuse that with depth data. And now you have a robot on that scale, that's taking maybe 50 or 100 watts or something when it's running. They could start to perceive the world like a person can. And you fast forward to now, and Intel's at the forefront of this, and we're using their Movidius chipset. We're getting to the point where you can actually have embedded systems do this. So, we started with, companies that had hundreds of millions of dollars of computers. Those are the only ones, say in 2012, that can harness AI. 2017, you're talking about like a couple MacBooks. And then now we're getting to the point where you can have some tiny thing doing that capability. So having depth perception, having artificial intelligence and computer vision all combined together. And that's where we are now. So that's the brief history in preparation for like the confluence of things that we ran into. Start with the why of everything we're doing. Spatial AI is crazy powerful because you're mimicking human-like perception. You have depth perception, just like our two eyes. You have AI to know what things are. And the fusion of those gives you that capability to perceive like a human on a small device if you can embed it. But there was no way for that to be tiny and light. And the problem we were trying to solve, so this is me trying to solve it with a bunch of my friends got run over, which was unfortunate, by distracted drivers. And so I was trying to see, okay, well, could you build a thing using depth perception and AI that knows when something's on your trajectory? And I was not wanting to repeat the situation where the Volvo CEO is detecting he hit a pedestrian detection system on a Volvo. I didn't want to get run over by my own system malfunctioning, so I sprinted at cars as well. And so this is the first thing that showed me the power of spatial AI. So I was using depth perception and AI together, all kludged multiple sensors. So I was using a depth camera, I was using an AI processor, using a computer, using a bunch of hardware to tie it together, and CV functions and everything. To mimic human-like a vision. So, what are you looking at? Where is it? That's now possible, right? And that's what I was able to prototype really quickly, but it was big and heavy and took a lot of power, and it was expensive, and it was not embeddable. And so the problem I was trying to solve, first off, I wanted to know, could you just solve it at all with modern technology, like the state of AI and depth sensing and stuff? And the answer was like, for sure you could. It only actually, once I finished zip tying all that stuff, like writing the code actually only took like half an hour because it was you run the object detector, which car was already a trained model. You have the depth information. In this case, it was from a RealSense camera. You fuse it together to get the 3D position, and then you get the relative trajectory, and you can tell if something's on your trajectory. But the problem was it wasn't embeddable, and I was wanting to make a bike light that could just tell you if cars on your trajectory for bike commuting. All the folks in my network who were hit were riding their bikes to or from work, and so every day they'd have 500 cars safely pass them for decades, and it's just that one car that's on your trajectory. You want to know, and that's the case. And this proved you could do that with all these advances since the 80s, coming to being able to do it on edge. And this was prototyped this in 2018, I think. And so this is somewhere between that laptop thing I said in 2017 to now this is like a Raspberry Pi with a bunch of other junk. But it's not embeddable. You can't really build a product around this. And so we set off to see, well, could you make an actual embeddable version? Does that exist? And the answer is yes. The Myriad X from Intel was the first thing in the world that allowed you to have all this stuff on an embedded system. And so you can see a US quarter there for reference at the bottom, and I'll hold it up to give scale. Hopefully my video is not too tiny. but you know, things are really small. And so the Myriad X was this really interesting chip, but given that it was so new and so bleeding edge, there was no way for, you know, just anyone, an engineer, to go develop something. So we found ourselves in this really interesting space that as engineers, we'd never been there before, which is when you go to solve a problem, like usually you'd like quickly discover like, oh, like that's a problem people solve. And you just buy a development kit and you like go solve it, right? And you go make it work in your application. Or you're like, well, that's against physics, or maybe that will be possible in 20 years or 40 years, kind of like the folks who were initially researching this in the 1980s for AI. You know, it caused an AI winter because they were like, well, theoretically that's possible, but it requires more computation and more time. With the computers in the 1980s, you know, the reason there was an AI winter is they said that will take more than all of the rest of human history to train a single neural network, right? Based on 1980s computation. And we were in this weird state where it was neither of those, right? It wasn't like this is completely unsolvable or this is by a dev kit. We're like, this is solvable, but there's no dev kit and the chip exists. And so this Myriad X was designed to be all these things. It has, it's embeddable. It's a little embedded system. It handles high resolution, high frame rate you'd need. It has depth perception hardware built in. It's got greater than 30 frames per second AI with object detection and semantic segmentation. And then it's got the computer vision to tie it all together on an embedded system. So it actually was a lot faster and more performant than those multiple MacBooks in 2017. And gave you the depth of vision and handled multiple image sensors, 12 megapixel image sensors and 1 megapixel depth. So it was exactly what we needed, but there was no development kit. And so we built the development kit and we built a series of products around that called the Opencv Ai Kit. So here's one of them. And we were in this space where for months, we were just like, this is the chip. When's someone going to make something useful so we can like use the chip, right? Like we want to use the chip. And so we were just like scouring the internet, seeing what we could find, talking to everyone. Like at one point, like I heard there was someone close to me, like a 2-hour drive away that like knew something about it. And I instantly drove there and waited in their lobby, right? Like we really wanted this to exist because, you know, it would be so useful for us. We absolutely needed it. And we thought it'd be so useful for the world. And nothing existed, and we found that no one had any plans to make anything exist. So we either needed to just give up, which I tend not to do, or build the development kit. So we did that, and while you're doing that, like when you're like, why isn't anyone making this? And everyone's refusing to make it, and we're spending months trying to figure out who's going to make it. And you decide to make it. There's this weird time where you're like, well, are we just doing something super dumb? Or are we like really on to something? And so we launched a Kickstarter, and that was the first time we really like kind of got that answered, that people were like, yeah, like we need this too, right? Like, why isn't this a thing? This chip would be so perfect. So launched the Kickstarter, and that validated that folks wanted to be able to have an embedded system that had all these capabilities and did want to be able to use this chip, which was the only chip in the world that so far that could do this. The team, the Movidius team and Intel team, were way ahead of their time, and the guy who started this chipset, also saw this in like the early 2000s or late 90s, that this was the thing that was coming, and had been working his whole career to make this. Myriad X was the culmination of his career in that regard, and so he was of course stoked to see that someone actually made it so folks could use it. Besides, billion and trillion dollar companies who were using the chip beforehand. So we launched the Kickstarter, and for this type of device, all the categories that it fit into, it broke all the records. So for any like printed circuit board, it broke the record. For an AI project, it broke the record. CV project, it broke the record. Depth sensing project, it broke the record barely. Occipital, who I mentioned, had the record previously, and they raised like 1.2 million in 2012, and we raised like 1.3 million. So technically, with inflation, they probably still hold the record. So we did that, validated that people wanted it. So then the question is like, how do we actually access this? How do people take advantage of it? We really wanted it. And so we built what we wanted to find on the internet, right? Which is like, we didn't want to have to talk to some sales guy. We didn't want to have to put like 100,000 or $500,000 or $20 million down just to prototype something. And most importantly, we wanted to be able to customize things, because when you're embedding something, you don't necessarily, like, maybe you want to buy one of these, like maybe you want like a little thing and this like happens to fit. This is our OPD light. But there's a lot of cases, in our case specifically, like we wanted to build something with it. We didn't want to buy a finished product. We wanted to build something with it. And specifically this smart bike light on the right. So we made it open source, MIT licensed hardware, software, and AI training so that anyone from a student, we've had high school students build custom hardware around this, could go build their embedded system. And so now it's this whole ecosystem of that. So these are all, everything you see here is open source. And the way, which begs the question immediately, how do we monetize? So we do all these open source designs, and then we have a system on module on there. So when you go to build something, we're just in a component on the design. So like you're buying a inductor from Murata, and you're buying a TRX-COM, Ethernet, or what have you, and then you're buying a Luxonis system on module. But we try to keep that as small as possible, and then folks can customize and integrate into tiny things easily. It's open source software as well. There's all sorts of applications out there that you can use. Open source AI training, and then also like one of the things that we're most excited about is how is it actually like open source? How do you integrate it? So it's open source at the software level. So you can integrate it with a Raspberry Pi or something that runs Linux or Mac OS or Windows or some OS we've never heard of. But it's also open source at the embedded level, at the microcontroller level. So one of the products, they all use the system on module, but this one has an ESP32 on it, on which you can run MicroPython. You can run other drone control algorithms, stuff like that on a pure embedded system. And then to the what, like I talked about, wanting it to be embedded, performant, spatial, with artificial intelligence and computer vision. This is our OAK-D model, also open source. And then, as I mentioned, the system on modules, these are what allow you to integrate this into what you want and customize any of this hardware that I showed here. And we have standard models. The reason for these is some folks do just want to put these directly on a drone, right? Like you don't want to customize it. You just want it to fly. So, here's Oak One. You can think of this as, here's the existing solution. You buy a camera, you buy an AI processor, a Pi, and then maybe some controllers. You tie it all together. This combines the camera and the AI processor into one device. And we have the embedded version that I showed you that then also has a microcontroller built in. And then OAK-D is the 4K camera, stereo depth, and the AI processor, all those building blocks that I talked about into a single device. And then, probably more interestingly than all of those are super interesting for if you already have some Linux system on your micro drone, for example. But some of these drones, you don't want a Linux system, right? Like that adds weight and cost and power. And so we have this IoT series, which is all of that. It's all of the processing that I talked about with an onboard ESP32, which then can be used to run embedded code. So folks have run micro-ROS on it, for example. And on all of these, then it's OpenVINO compatible. So you can do object detection, face, vehicle detection, pedestrian, text detection, and a bunch of stuff that we can't even think of. And the most important for drone applications, and really all of this is like the crux of everything, is you can run AI so you know what objects are. And so this little GIF shows it's detecting me. This is colorized depth, and then it's detecting the chair, so you know where objects are. And then you can also use that point cloud information if you want, or run a class agnostic object detector, which can run on there, which allows you to detect objects even if you don't know what they are, right? Like there's some object that's in front of your drone, you have no idea what it is. You can still use an AI model to detect, hey, that's an object and it's in this position, which can be really useful for not having to parse point cloud data, because parsing point cloud data to detect there is an object can be painful, because you have to think of like, how do I classify something as an object and avoid it? There are class agnostic object detectors that you can use. And so in the embedded instance where you don't have a host processor to do logic like that, you can run one of those, combine it with depth information and do obstacle avoidance or tracking. Pose as well. There's some cool examples where you can do like hand tracking, you can do person detection, then you can zoom in, then do pose to find like a wrist, choose which wrist you want to talk to, and then you can find palm, run a palm detector, And then you can do like sign language and control your drone in 3D space. So there's some examples online that we can talk about in Q&A. Semantic segmentation's really nice as well. You can do semantic depth, which is really nice for navigation as well. And there are all sorts of possibilities here. So you have 3 cameras, a pipeline builder that allows you to run arbitrary AI and depth processing. And so you can do things that, we didn't even think of. Like we have customers who've run depth between the color camera and the grayscale, customers that run AI models in parallel. So you can detect the position of objects that standard disparity depth falls apart on. Like imagine a bunch of like mirrors in a field, right? Or like you've got mirrors hanging. Disparity depth's gonna fall apart on a mirror because it's gonna see the reflection and think that thing's, maybe the reflection's 50 meters away, and then your drone's gonna fly straight into the mirror. When you run an AI model in parallel, it can still know the location of a shiny thing, which disparity depth can't. And so this is an example of stereo neural inference where you can see I'm actually in different positions, and then it's doing facial landmarks, so my eyes, nose, and like edges of my mouth and stuff. Here's an overview of the features. So, running AI, getting location of things in 3D space, tracking those things. So I'll have a demo on a drone later about that, tracking in 3D. One of the things that we are super excited about and is you can encode directly on board the camera in parallel to all these things. And that's super useful for when you actually go to deploy and you want to know what the heck happened, right? You don't have to record, raw video. So it takes it from raw video at 4K is like 800 megabytes a second, and encoded at H.265 is 3 megabytes a second, which is, you can even write to like a pi 0 really easily. You can do lossless zooming, which is used a lot for when I was talking about finding a person, then finding like where their hand is, and then doing hand pose, and a whole slew of other things like in JPEG. So then, what is this actually made of? So we're just simplifiers, as in my bio, right? I'm a huge believer in innovation, which is the steam engine was invented by a technician in a basement, right? Not a guy who worked at a billion-dollar company or a market cap leading company or anything like that. He was a technician in a basement. And the reason he was able to invent the steam engine is he had these easy to use tools and he was able to combine them in interesting ways. So the Myriad X is the underpinning of all of this. We just simplify it and we make it so someone who's a technician in a basement can go do something really cool, right? To make it easy. So, it has 4 trillion operations per second. It has these vector processors that allow you to run all sorts of different computer vision really fast. It's got these dedicated vision accelerators. And that was, no pun intended, the vision of this chip is, if you have a general compute platform like a MacBook, you can do all sorts of things, but it's not super efficient. So, and in a lot of these vision situations and perception situations, you already know all those tasks that you're going to do. So what if you just put those in hardware, like disparity depth in hardware, depth sensing as a hardware block, edge filtering as a hardware block, like optical flow and motion estimation as a hardware block, feature tracking and orientation as a hardware block. So it has those vision accelerators. And then it's got this crazy memory bandwidth to tie those all together. And then of course the neural compute engines give 1.4 tops of AI processing. And then on these models, which again are open source, so you can actually use different image sensors. There's a 12 megapixel. We found that was extremely useful so that you could just punch in, AI detects one thing, then you pull a high resolution out of that, it detects that, pull a high resolution out of that. And, 30 feet away, you're still like reading sign language off a hand. And then global shutter grayscale, so you can get high resolution depth. There are options for this, and we have open source reference design for all of these. So this is one of the standard, it's 1 megapixel depth. This smaller, lighter version is just 300,000 depth points. And then we have a higher resolution, which is 2.3 megapixel depth. Really easy to get up and going. So we have installers. You can just do, apt-get install on Ubuntu. The Windows installer is super easy. And then maybe more importantly, there's this whole community that we're developing. This all goes back to like the thing that we wished existed so we could develop our product easily and quickly. So we decided to take that upon ourselves. And then, finally, like where is this used? So tiny aerial and subsea things are a big one. Obviously for this conference, that's super relevant, but generally just tiny things where you want an embedded system, but you want it to have all these like human-like perceptions. So, spatial AI and CD all together. E-scooters, micromobility, that one's actually kind of counterintuitive. One of them is, what we originally did or wanted to solve, which is keeping people who ride bikes safe. But there's also flipping that on its head, which is people who ride e-scooters in downtown cities. Most of them are respectful, but there's, always that jerk who like buzzes through people going really fast and unsafe and goes around blind corners. So you can have this installed in an e-scooter and know where people are and just automatically slow the e-scooter down. Visual assistance is really cool. This is human-like perception on a tiny device. So if you have visual impairments or you're outright blind, this can be a huge help because it can tell you where things are, is the vehicle on your trajectory, or you're about to walk across a crosswalk and so forth. There's some really cool bleeding edge research going on there. Cargo, transportation, autonomy, all sorts of, how full are things, what's in there, is it completely empty? Sports monitoring, this has relevance with drone too, because you can punch in quite a bit. You can zoom in. Smart agriculture, all sorts of safety systems. In agriculture, you can imagine, you know what things are and where they are. Picking strawberries, for example. Safety systems is the hand about to go into a wood chipper. Security, one of the applications is actually doing gun detection, and you can do it privacy first because everything's processed on the embedded system and tells you where a gun is. So you can just literally have a map of like there's a shooter, which is a problem potentially unique to the United States. And then microsatellite sensors, because you can do everything on a little embedded system. So then micro drones, we'll focus on that. Maybe drone isn't the right term, but let's see if this will actually play. Okay, cool, it is. So here's an OAK-D. This is obviously a bit of a bigger drone that was prototyping on. But the IoT, for example, is really small. The OAK-D light's really small. And so this shows running depth perception and a custom object detector trained for drone landing. So you can see there, it's finding the X, Y, and Z position, and it's actually guiding the whole drone. And then I'm going to see, excuse me for a second, turn the sound off on this. I'm sure you guys are very used to the sound of drones. So it's finding the target and then, auto landing based on that. So it's using the depth perception and AI. And the next thing that is being worked on this is doing all of this on an IoT version. So you don't even need a host computer, except for if you just wanted to visualize. So that's one example, precision landing. And then another, we've been responding to the drone community. When we first made this, we actually didn't think the drone community would want it. We see so much, from so many big drone companies, and one of the few companies that actually got access to the Myriad 2, which was the precursor to the Myriad X, it didn't have nearly as much AI capability, didn't have a depth engine, was DJI. And so we figured, well, are we really going to add value? Like, it seems like drone folks are covered, but actually there's a huge response because the ecosystem is customizable, so you can make what you want. And so one of the somewhat recent tests actually was we had an autofocus module in there because there's a lot of locations where you'd want to autofocus. So the default hardware was autofocus. So you can see on the right here is autofocus. And depending on how many vibrational modes and the amplitude of the vibrational modes you have on the drone, it can really mess with autofocus because the autofocus is it's electromagnetic controlled. It's a free moving lens, and the electromagnetics hold it like a speaker is moved. And so Rishab there at ArduPilot sent us this back, and we're like, well, that looks terrible. And so we worked with ArduCam, who's extremely responsive, and we love those guys. And they made a fixed focus version of our color module really quickly. We sent it back out to Rishab, and he was like, oh yeah, this is a million times better. So now we're offering everything in fixed focus variants as well. So everything can be ordered. And actually, he got us this information just in time for a Kickstarter, so that we worked with ArduCam, and it turned out about 70% of folks who ordered our OAK-D Lite, which there were 11,000 ordered in those 31 days, actually wanted fixed focus because they were putting them on drones or other heavy machinery, or drones aren't heavy machinery, but other things that vibrate like heavy machinery does, and lawnmowers and so forth. So this is an example, and you can see how it's just, you know, night and day different. Obviously, the 12 megapixel camera is still rolling shutter, so you can see a bit of like blurriness as an effect, but you know, it's still a ton better, and you can see the object tracker in 3D position a lot better. When this demo was run, this was actually debugged on our Discord. We have a Discord where there's a large community of folks who can communicate and prototype and debug. The threshold for distance was set wrong, so it was not allowing distance measurements above, I think, like 4 meters or something. So that's why the distance measurement is wrong on the bounding box on these, but you can see it's way better. So yeah, that's the IoT version actually is on the top there. Let me pause this, excuse me again. The IoT is on the top there, and that just happened to have an autofocus and then the fixed focus, but both are orderable with fixed focus. And this is Rishab, you know, his next objective that I wanted to present. This is, you can see it's very recent. That was 2 days ago. Someone was asking him, you know, why are you doing your next approach? And, you know, he says the IoT version is really interesting because it's the first time you have such interesting applications without a companion computer, which is our, you know, one of our core objectives, right? Robotics is the big one. UAVs, drones we view as, you know, flying robots. Right? That's fundamentally what they are. And embedded robotics is our core focus. And so that's what he's going after. That's what he's building in ArduPilot. And on the right there, you can see one of the Opencv IoTs, where then that could be literally the whole thing on the drone that also just straight up controls the drone, which goes back to research in this conference, which is super exciting. And then on the left, you can see progressions. So all of these are actually buildable, especially since it's open source, in an IoT version. So it could be standalone. You just have IO that goes to your motor controllers, and it just flies your drone. So if you have some application, and say you train a neural network, custom neural network, you can just fly your drone directly, nothing else involved, which is super cool. And then to cover other applications of visual assistance, for example, here are some prototypes that are made. It's showing, you know, the crosswalk is ready to go. Is there a car on your trajectory? Those sorts of things. Precision agriculture, which also, you know, relates back to drones, because you can have the drone guided based on like what it's seeing in a field, right? Instead of flying the whole field, it can, you know, spend more time focusing on where there are issues. Health and safety, knowing where people are and where their joints are and so forth. And then, you know, this is a system we want to allow folks to just get up and going, where you don't have to do a bunch of work. So you can just buy this online. There's Amazon Prime. Unfortunately, we don't have Amazon Prime in Mexico yet, but we're working on it. But I think you can still go on Amazon and they'll just ship it to you, but it's just not as convenient as if it was Prime native to Mexico. But soon, Mexico and Canada are the next two. But then it's also open source on the right here. You know, you can look at designs, you know, folks who design hardware or hack hardware can then, you know, go build your own or modify it or what have you, with the purpose being, you know, we wanted this, right? Like we wanted this to exist. We wanted it to be easy. So we tried to make it as open source as possible, so that folks can go solve their problem, you know, without being encumbered with talking to some sales guy and him trying to pitch you on, you know, $100,000 deposit on a license or something like that. And then on the left here, so we are still in pre-order stage for this Opencv Lite, and actually on our campaign, you can see it's on a drone. This is one of the, you know, better products for going on a drone because, you know, since put a sense of scale, I do have a very large head, so it's kind of like cheating, but it's pretty small, right? And so that's one of the, we found out in the Kickstarter, one of the core applications, by the fact that in our survey, most people, we asked folks, do you want fixed focused or autofocused? And the number one response was fixed focused, using it on a drone. And so this is still in pre-order. Apparently we have 8,415 people as of when I screenshotted this. And all the others are readily available. Although we've been seeing a lot more sales recently, so stuff's been stocking out, but most of it is findable if you're just willing to go hunt a little right now. And I think that's it. So here's me walking at one again. I always like to give more time for questions in case I missed. So I figured now would be a good time to open it up for any and all questions.
Great, thank you, Brandon. Very nice talk, and it's quite interesting. I like this video of the precision landing. We have done a couple of papers on that, and we have used the standard camera. You know, the one that we have with the drone, and then we did it on board as well using the Intel Compute stick. Mm-hmm. But it was slow. We have to say that, especially if we wanted to run CNN, a convolutional neural network, it ran at maybe 10 hertz, you know, like 10 frames per second. And then when we got this sensor and we began testing it, it was quite impressive because we could achieve from 30 to 40 hertz. So perhaps in that sense, what is the fastest network that you have been able to run on the sensor, if you remember?
Yeah. So you can have the fastest frame rate that OAK-D can currently do is 118 frames per second. And there are definitely networks that will run faster than that. And so you can do 118 frames per second currently on OAK-D. In the way like the nature of research is right now is, I was actually just on this Edge AI summit panel where we were talking about this, and there's only so much time, but fortunately we actually have time to talk about it here, where, you know, that machine learning researchers tend to operate in infinite resource land. Like they're training on the cloud, you know, they've got just almost infinite resources. And then folks who go build things, especially at the edge on a drone, are always operating in limited resource land, right? And then the folks who are on infinite resource land often are incentivized to use a lot of resources, because in that land, when you produce a research paper, the way you get attention is by being best in the world at accuracy generally. And it's kind of hard to even quantize like being faster, because like you can just be faster by getting a bigger number of infinite resources, right? And so you'll end up with these super heavy networks. And then you go to like port those to some embedded system, and you can like tune and make them better and so forth. But for the most part, a lot of the things, even the examples that we have available for the platform, are not yet anywhere close to like what you could theoretically do with the platform. If you convince one of those guys, and we've convinced one of those guys to leave infinite resource land and live in finite resource land. His name's Mattia, and he just joined and joined our company. And, you know, over the past 2 months he's been here, he's, you know, gotten probably 100-fold the number of models running on our device than we had in the past like 2 years. And so I think, you know, soon, probably like 2022, you'll start to see models that can run at you know, frame rate limited on the device, so, you know, 100 frames per second. And then OAK-D Lite are lower resolution grayscale cameras, and they can run at 200 frames a second. And so then it's this game of, you know, the standard models will run at like 30 or maybe 40, like you mentioned. And then as you start to bring this research, because it's kind of a newer field of like, you know, limited resource, high frame rate, you know, machine learning training and architecting and stuff. And there are these like PicoDet and stuff like those. We haven't gotten those running to my knowledge. Maybe he did, and I just didn't notice yet. But those are very likely to be able to run at sensor frame rate, but we're just not there yet. So yeah, 40-ish, 30-ish, depending on the model. Semantic segmentation, we can do 30, but all of those, there's a lot of room to bring in, you know, it really optimized models. So yeah, you know, hopefully we'll have, you know, object detectors that could run at 200 frames a second. And so then we can already get depth on OAK-D Lite at 200 frames a second. That's this little guy. And so then theoretically, if, you know, everything aligns, you'd be able to have depth at 200 frames a second and object detectors at 200 frames a second, which would be really cool.
Great, thank you. And yeah, one of the things that in my lab we wanted to use this sensor for was for visual SLAM, you know, simultaneous localization and mapping. And I mean, not only talking about using neural networks, but then exploiting the fact that we have depth, like almost for free. It's like a depth camera. But then on the top of that, you also have the color camera. So we are exploring how to combine visual SLAM and at the same time try to detect like semantic objects or do semantic segmentation with the color camera and then enhance your map with that. So because the idea is that if the sensor can do that, like the segmentation and the depth, and we just use it for rapid SLAM mapping, then not only for drones, like for robots in general, robots that have to navigate in a space. So what are your thoughts on that? Like, what experience have you got with this type of applications?
Yeah, I think I've seen some of your work on that, which is awesome. And yeah, I think it's a fantastic use of the platform. In fact, one of our engineers who joined, he applied to the very first Opencv AI competition, which was in 2020. Yeah. And his submission, which was amazing, was, he wanted to do SLAM, which was like AI object detection or semantic segmentation, augmented SLAM. And on the interview with him, I was like, yeah, we should do that, but you're going to have to do horrible tasks first, right? Like our factory calibration and all those things. And so far I feel bad. And we just had a conversation about it. He's been very much so on like, making it so when we make 11,000 of these, they actually show up properly calibrated. But it is something that we're extremely interested in doing and wanting to, get a little bit off of like this horrible tasks, as I describe them, to doing that. So, one of the aspects of that is actually, outputting, doing VIO directly on the camera, which we want to do. And then, let's see, VIO, and then exploring just like, what are the limits of doing that? And like you mentioned, having AI on board helps you to do, loop closure at lower cost. It helps you to like reorient, because you're like, okay, well, I saw that coffee cup, right? And like I saw that coffee cup and its pose, or I picked up these specific features, and there's a whole ton of interesting possibilities there, because maybe a coffee cup isn't the best way to reorient and loop close, but there are common objects, say in your use case, that are, right, like where you can learn, okay, well, these things have big baselines, and I don't know what they would be, but like big baselines in this situation, and you can find features on them easily. And so once you've done that, you can orient and distance very well, and you can, full 3-dimensionally loop close. So yeah, I think it's a huge opportunity for the platform to allow that, and I think it's extremely useful in robotics, in UAVs, pretty much anything that has to navigate in the physical world. So far, our platform is kind of just given some of the basis functions for that, but we haven't gotten into it itself, although we really want to, like you mentioned, depth, and then we have algorithmic feature tracking, which helps, but like AI-based feature extraction and then labeling would be extremely useful. And so that's another part that would be extremely useful for generating a great SLAM. Is it's not just, okay, there's some features and we don't know if they're right or wrong, or when we lose tracking or not, but like that is this feature, we know what it is, and we can hold on to it, and we can re-identify it even when we re-enter the frame, right? So yeah, I'm super excited about that stuff, and we're kind of chomping at the bit to actually be able to do it. But we know, our customers of ours and folks who are building off the platform are doing it. So some of those, there's very initial attempts at it, like open source, and then we know there are customers who are building closed source things, and we're excited that they're using our platform to do it. But there's part of you that's like, I wish that's open source. So yeah.
Great, thank you. We have a question from the audience, so let me read it to you. So this is a question from Murat Bronze. I hope I pronounced it well. He says, I was wondering if Brandon can make a fast comparison with FCE-BUAP or FCE-Voice. Do you know that device? Or
yeah,
I don't know
FCE-BUAP. So it's, all this stuff is so, multinational, right? I was on the call recently, and someone mentioned it, like, oh, all that was made in Russia. And I was like, yeah, I mean, when we're literally riding and at the front, all of us, whether it's folks who've been studying this for a long time or folks who are brand new to it, we're at the forefront of human capability. Like this is a lot of like the fruits of the labor of human capability, and it's constantly moving forward. Yeah, Jervois is awesome. I have one. You know, our niche is you know, having AI, which is what Jervois does. AI, Jervois and Opencv, for example. So our thing is like 5 things, right? So it's embedded, you know, embedded system, like we talked about, as you all know, performant, which falls into multiple things. So multi-sensor is probably one of the most important. High resolution and high frame rate. High frame rate's a really relative term, but to put numbers behind everything. Multi-sensor, so like 3 or 4 cameras on a device. You know, most of our stuff are 3 cameras. We have customers that are doing 4 cameras, 4 image sensors. The performant aspect is in high resolution. So this is 13 megapixel plus, you know, 300,000 depth points. We have other systems where they're doing 4 12 megapixel cameras on the same platform, or 4 2.3 megapixel global shutter. So that's the performant aspect. And then high-ish frames per second, right? 200 frames per second on OP light. So we're talking about 5 things: embedded, performant, spatial is another big one. So the only reason people really use our stuff is if they hit 4 out of the 5 of these. If they hit all 5, they're like, yeah, I super like that thing. So spatial sensing, disparity depth is all the products that we have right now are disparity depth based, which is the same as human perception is disparity depth based. AI, so onboard AI acceleration, and then onboard CV acceleration to tie it all together. So if you look at like Jervois, it's very similar, right? But it's embedded, AI, and CV, right? But Jervois doesn't support multi-image sensor, right? Like you just buy, it's got a single camera, right? And so we saw Jervois and we're like, that's great, but for our problem in solving the bike or like the distracted driver problem, like we needed depth information, you needed to know how far away the car was. And someone would argue, well, you know, why don't you just do what Tesla does? Like they use a single camera and they extract depth, right? From a single camera. And that's a viable solution, and it's a trade space. But the trade is if you have a ton of computation available and a lot of power, and you don't want 2 bumps on your Tesla door, you just want 1, a single camera is great. But the trade is like a depth estimator. So out of those, like that's missing on Jervois, that, you know, there's no depth. A depth estimator that's going to do a great job in real time takes maybe 25 trillion operations per second, right? And so our whole platform is 4 trillion operations per second. And so whereas doing depth algorithmically takes like 0.01 trillion operations per second if you have 2 cameras. So when you look at Jervois, you know, they're embedded AI and CV, missing multi-image sensor, that's just not their focus, right? Like we're different than that. And then they're they don't have, you know, depth information. And so that's really why folks would choose us. And then Opencv is the same thing. So embedded AI and CV, right? They don't have multi-image sensor, they don't have, you know, super high resolution or high frame rate stuff, and they don't have depth sensing. So that's largely the difference. Those are great platforms. If you find yourself needing embedded AI and CV, Jervois is a great choice. Opencv is a great choice. I don't know the Jervois founder, but I think it's a great product. I know the Opencv founder. His product's great as well. And then if you find yourself needing 4 of the 5 of embedded, performance, spatial, AI, and CV, then we're a platform for you. And I think all of these 3 platforms are open source. I think Jervois is, we are, and Opencv is as well. Generally, if people need 3, they use Jervois or Opencv. If they need 4, they'll typically use us. If they use 5, then they send us thank you letters, if that makes sense.
Yeah, he does. And actually he says, perfect, thank you very much. And now that we are talking about comparing against other cameras or sensors, in the last years, maybe 5 years, there is this camera that has become very popular in the robotics community, the event camera.
Oh, yeah.
So I was wondering, what do you think of that device, and how does it compare to what you are offering?
Yeah, so we want to get a hold of like an event camera image sensor so badly. So if you guys like know how for us to like buy one and put it in the platform, we'll like release an open source design around it and we'll get it integrated. So event cameras are so incredibly useful, and we found some. Argicam has found some for us, but the ones that we found that we could actually purchase are relatively low frame rate, and their intention of these because there's a spectra of event-based cameras. The ones we want are the ones that they're like effective frame rate are like 5,000 hertz. Because if you get those, and I know those are commercially available, you can just do insane, like nutso level good job of SLAM. So all the things we were talking about, we have an event-based camera, we put that, slap that in, and that's the fourth image sensor out of that performant thing, right? So you have depth information at 200 frames a second. You've got effectively motion overlaid at the depth, interpolate that's actually in between all the depth frames at 5,000 frames a second. Like that's insane. Like your SLAM will be so accurate. And when things are vibrating or whatever, like it'll understand all of that. So the ones that we've been able to get access to so far are like 30 frames per second, which actually doesn't buy you anything in our case, because our cameras are already 200 frames a second and you can do differencing on them. But we were like super excited and desperately wanting to buy it. And then we did the analysis and we're like, that doesn't actually get us something. So we for sure want to do it. Now it begs the question, what are the 30 frames per second event cameras? What are those for? Those are great for privacy applications. So the ones that we've been able to find are privacy, where they literally just want a security camera that you can put in like a hospital room, and that has applications. So we may still build something off of it, but it's less relevant to drones, right? It's less relevant to SLAM. So if anyone on the audience knows of those that we could buy, we've seen those. Like I think Samsung for a while was producing a sensor that had those rates for event cameras. Anything 200 frames per second faster as an event camera, we'd be super interested in, because it's so helpful in SLAM. And that's the first big use case that I see for it. For the high frame rate, low frame rate is privacy. I think there's a lot of discovery that can exist on that. And when you look at it from like a biologically inspired perspective, I like to think back in that direction, because out of billions of years of evolution, a lot of things have been tried. In our eyes have event cameras built into them. So when we think about what our mission is, to embed a lot of this into the sensor effectively, our eyes do a lot of that. We have edge filtering in our eyes. There's some research, I wouldn't be able to find it because it was from like 2 decades ago, that show they can actually show you what the world would look like to you if you didn't have edge filtering applied. Like we actually have very aggressive edge filtering applied in our eyes, and we're just used to seeing the world that way, because that's the only way we've seen the world. And you can unapply it, and there's amplification and so forth. But then there's also like event camera types of things that's built into our eye as well. That's how we can pick up things in our peripheral vision. So I think it's a key building block that we've kind of been missing. So I'm super excited about event cameras, and then just chomping at the bit to figure out, how do we get access to one, and how do we continue our mission, which is to make this stuff easy for folks to use, which the first aspect of that will be, how do we find one? How do we actually?
Great, thank you, Brandon. Yeah, it would be very interesting. So there's another question from the audience. So what is needed to get the cost of event cameras down, in your view? How can academia participate?
Yeah, unfortunately, I have no idea. I don't know the architecture well enough. In terms of, so there's like 2 aspects of getting the cost down. One is like literally the cost of producing the thing, and I have not the foggiest. I have no idea. Then the second aspect is, if someone figures out how to make a relatively low cost, event camera image sensor, we can do the same thing that we've already done, which is like, the Myriad-X and all these technologies were in the hands of people with tons of money to be able to do these things, and they were the only ones that had access. Whether it was just literally to pay a bunch of money, or it was too complex to use, or it required too much specialization, we can help in that cost standpoint by just getting it out to folks. But I don't know enough about event cameras or just camera production, like the image sensor production in general, to provide any answer there, unfortunately. Sorry.
Okay, yeah, I'm the same. I wanted to ask you as well about this other camera. I don't know if you are aware of that. There is this camera built in Manchester University. It is called the SCAMP sensor. Does it ring a bell to you? So the idea is that each pixel is a processor. It has a small processor.
Okay.
So they're going to the other side, opposite to what the event camera wants to do, because the event camera is a sensor for very basic detection of motion, right? Like if a pixel changes in intensity, then it triggers something. So then if something moves in the frame, it will spike this pixel, only those pixels, and that's it. And that's why it generates loads of events. This other group argues that, yeah, that's something that maybe the eye does, but that is still quite low level, because then we have to reinterpret all that amount of data. Yeah. So what these people are saying is that it would be better to process each pixel, like exactly what you said, right? Like if we want to apply filters, we do it directly on the pixels. Yeah. So it's a totally different approach. It's not yet commercially available, as far as I know. They are still in terms of prototyping, but they have shown things like running neural networks with these small processors for each pixel. They have used it for autonomous drone racing. So yeah, maybe I will send you the link. I know the professor who is responsible for the project. Piotr Dudek, I think is his name. Well, I will send you the details. And they have collaborated with the University of Bristol, where I did my PhD. Okay. So with my former boss of the postdoc. So that's why I know them. But that is also another interesting approach. And I was wondering whether you have any ideas as well regarding this idea of having processors for pixels, or one pixel or group of pixels.
Yeah, I think it's a fascinating idea in like covering the trade space of like making new things like this that are, approaching human-like perception. I think one of the first things that's worth exploring is, how do humans do it and how do other species do it, right? And what you're discussing here, I think it is in the eye, right? Like it's flexible and it's not a full brain, but there's a lot of processing in the eye. And so I think it's for sure a worthwhile path. And I think there could be a lot of interesting things. And then in addition to, exploring what, human perception has done, as we've seen in other technologies throughout history, like airplanes, for example, you observe what nature does, you take some interesting things from it, you observe what fish do, you take some interesting things with it, and then you build an airplane, right? It's not at all what a bird does, right? But with our set of technologies. And so I think not only is that worthwhile from like the biologically inspired, but I think there's a high probability out of that research that something that we don't do as humans, because it doesn't work well when you're made of carbon in transitioning to silicon, to discover new things that don't work on humans, but will work in technology that maybe are kind of like analogous, if you will, and extremely valuable. So yeah, I'm super interested in that research. I think there's a lot of fruit to be had getting this processing as close as possible to the image sensors.
Great, thank you, Brandon. Well, the last thing I would like to say, because people have asked something else, so I will take the opportunity to tell you this. The reason why I thought your talk would be very interesting to this community is because in these events, we don't only have a conference, we also have competitions. It's unfortunate that because of the pandemic, we didn't manage to run the competitions. We wanted to do it here in Mexico. It would be the first time that many people would come, but well, next time maybe. Yeah. But in the past, we have got competitions, and there are indoors and outdoors competitions. And there are several challenges where I think Spatial AI is needed. So this calls for smart drones, intelligent drones. That's how I call it. So this conference offers a good mixture of aeronautics, like very nice designs of drones, and then this other side, which is like robotics for drones, for aerial robotics, because then we have missions where the drones have to enter a building. I remember one of the first competitions we attended in China. There was this small house built in a gym, and the drone had to enter the window, either the window or the door. And we used a SLAM just to follow waypoints, but the clever way would have been just to detect the window or the door, right. As you enter. And there is another challenge, which is whether the door is open, right? So, and things like that, like counting people, or if you want to deliver a parcel, to do the precision delivery, you need to identify the spot. And if you run all of that on board, then this is the type of technology we need. Yeah. In our project that we submitted to this Opencv AI competition, we did warehouse inspection. And that was the challenge of the IMAV 2019 warehouse inspection with drones. And we did it with our Intel stick computer, a conventional camera. But yeah, it was really, really hard. And then we got your sensor, and it became quite easy, you know, just to implement everything. So anyway, that was the reason why I thought your talk would be very interesting to this community. And I thank you very much. I'm deeply honored to have you here, and I hope
thank you.
Yeah, you also enjoyed the time.
Yeah. And then actually, I know we're literally on the last minute, but one thing I wanted to mention is, you know, in the spirit of that competition, one thing that we've seen that would be extremely useful to the community now that we've built like a layer is synthetic training. So what we're working, you know, really intensely on right now is combining Unity. Unity's working on this intensely as well, and we're getting a lot of the fruits of that, getting a virtual OAK-D and our whole line into Unity. So in that house example, like if you know the specs of the house, you can literally make it in Unity, get, you know, 2 million views of it, train your object detector or semantic segmenter and refine a model, and then literally have trained models that have seen millions of views of that house, all with synthetic data. And you can augment the house to be different colors and different lighting and all sorts of stuff because it's all in simulation. And you have the 3 views and the depth information and so forth. And you can show up to a competition where you're just like armed to the teeth with specific models that understand every aspect of the house, right? And that's one of the things we're really excited about, like in the warehouse navigation and so forth. You can make these scenes so quickly, and having the capability to do SLAM and to record this data, make SLAM, you can literally go, you know, fly a drone, record all the information, recreate that literal warehouse in Unity, right? And then you can augment it, change it, so that you can, you know, synthesize all sorts of different permutations, so that it'll work in different warehouses, different competitions, and so forth. So that's the thing I forgot to mention in the presentation is kind of what's next in a lot of the Unity based simulation and synthetic training, synthetic testing, and everything with the platform. I think is going to be super valuable, and of course we'll, you know, open source that all as well.
Yeah, of course. And just one more minute, because after you said that, of course, I was thinking of what people from MIT are doing with autonomous drone racing. So basically, they are building these arenas, you know, the racetrack. I'm not sure if they use Unity, but well, they have AirScene, which is, I think, similar. So they are recreating these racetracks so that you can get access to loads of images. But then the other interesting thing is that maybe, I mean, for this problem is that how do you build the racetrack, right? You have to build the gates and all of that becomes very expensive. So, but if you had a virtual racetrack, and then if you have the space, like let's say an open field with maybe Vicon cameras or even a SLAM, then you can work out, given the position of the camera, you can work out what the drone would be seeing according to this virtual space. So, and that's why actually once I asked to one of your colleagues, I think, or to you directly, I don't remember, by email, whether it would be possible to send images to the sensor. So rather than using the images from its cameras, just to bypass it and send other images, because then we could do that. And you can do that. And funnily enough, in 2017, like exactly what you described, I wanted to build that as a company, which was, you know, making virtual races, right? Like you use SLAM, you use onboard processing, and then all you have to do is an open area, you know, that has some visual interest, which almost all outdoor areas have. And then you can make virtual courses that you can fly through in, like, you know, FPV, and literally have competitions that way, which I think would be really cool. And I think we're approaching the capability to do that now, with probably the current generation. I think you could build something with that, but it would be work. And then we're also working on our next generation, the next generation of the Myriad X, which is just faster at everything. So I could very easily see that being a thing in 2022 using this, which would just be, you know, so cool, right? Like you can have real life virtual racing effectively. Definitely. Brandon, it has been a pleasure and a privilege to have you with us. Thank you. Thank you very much indeed. We will send you a virtual certificate of your participation. But
thank you.
Apart from that, thank you very much. We are humbled to have you.
Yeah, thanks.
Take care. Bye. I apologize to the speakers of the next session of the session Control Systems 4, but we have Fermi Guerrero Castellanos as the session chair. Apologies again, but we got carried away. It was a very, very nice and interesting talk. Guys, if you are interested in these products or the sensors, please get in touch with Brandon. I'm pretty sure if you click on his image on the website, it will take you to the company's website. So Fermi, are you there? I can see Fermi. Yeah, there
Okay.
you are. Okay, you can take over. Apologies again, but it's only 5 minutes.
Okay,
Go ahead.
No problem. Thank you, Jose. Thank you very much for joining us in this last session of the second day of IMAV 2021. Now we have the control system session number 4, and we have 3 interesting papers. So we have the paper number 21, 7 and 17. So I think all presenters are here. So, okay. So the first one is the paper number 21. Christophe?
Yes, good evening.
Okay, so could you start your presentation, please?
Yes, certainly. Give me 1 second to share my screen.
Yes.
I will try to present for you the hybrid UAV attitude control. Of course, after such an interesting keynote, I hope you can still follow. And here is welcome to the presentation of the paper called Hybrid UAV Attitude Control using Incremental Nonlinear Dynamic Inversion and Dynamic Tilt Twist. The work was done by my student Lars Delleman, and I'll try to present his work as well as possible. For a long time, the research on flight control of UAV was focused on quadcopters because they are simple, cheap, and versatile. They have only 4 moving parts and therefore are a great study object. And fixed-wing aircraft because they have a very good endurance. They have a very good lift-to-drag ratio, can stay in the air with little energy and thereby achieve very long ranges and very high speeds. But recently, in the last decade, a lot of attention was given to so-called hybrid UAV. One of those hybrid aircraft is the Nederdrone. The Nederdrone was developed in Delft to be a versatile vertical takeoff and long endurance hydrogen-powered aircraft. The fuselage is shaped around a pressure cylinder with hydrogen, and in the rear, in the back, we have a fuel cell. It has very high aspect ratio wings for minimal drag and long endurance. And thanks to its 12 motors spread over the long wing, we have hover capabilities. So the objective of this study is to improve the accuracy of the position control of the hybrid Nederdrone for the mission of landing on, for instance, a moving vessel. And that moving vessel is typically surrounded with wind and turbulence. And one of the objectives of this study is to not need hardware modifications. It then includes running a controller on board the same autopilot with the same microcontroller, which excludes some of the most advanced control theories. The Nederdrone is now flying with incremental nonlinear dynamic inversion control. The nice properties of this type of control is it is sensor-based. You only need a good model of the controls, so a good estimation of the control effectiveness matrix, but you don't need a very accurate aerodynamic model of the whole platform, as the sensors, the accelerometers, are actually measuring the external forces on the platform. The implementation includes a linear model to create reference signals before it enters the IMDI control. And the work presented in this paper is about how to create effective reference signals for hybrid UAV. This feedback system can be done either in Euler angles. It can be done in quaternions. The quaternion is basically one rotation in between 2 coordinate systems, and it's mathematically the shortest rotation. Very interesting. And but recently another suggestion came up, which is tilt twist. This one splits the pitch and roll from the yaw, as in most helicopters the thrust vectoring principle is used for position control, and that has a higher priority than setting the yaw. But when flying in quaternions, the matrix multiplications correspond to the shortest rotation in between two coordinate systems. If we look at this animation here, we can imagine that the red block represents a thrust vector, a current state vector, and the blue block represents a desired state. A quaternion multiplication then provides the shortest rotation to go from actual to desired state. But if these blocks were thrust vectors, this does not correspond to the shortest rotation between the thrust vectors, which would be a rotation in the red and blue plane. And you can see right now that the yellow block in between states has a very big lateral offset. If we are thereby interested in position control, and the thrust vector is what determines how the position is steered, having these lateral offsets is not desirable at all. When does this happen? It happens in two cases. First of all, only when there are large errors, with tiny errors in the orders of a 1 degree roll and 1 degree pitch, the difference will be almost invisible. And the other part is, if not all three rotations can be executed at the same speed or at the same rate with the same response time, then the quaternion control runs into trouble, because the quaternion describes one rotation around one axis, but if the platform can rotate faster around one than the other axis, then it doesn't do what you expect it to do, and you end up with perturbations. In the case of the nether drone, which has very long wings, the roll is, for instance, much more controllable than the pitch, which has a much shorter arm, and the yaw, because of the damping of the wings, is by far the hardest to control. In such a case, tilt twist can come to the rescue. It was proposed by Beach et al. In 2014, but it has never been combined with the powerful sensor-based control of IMDI. Tilt twist starts by finding the shortest rotation to get from the current tilt vector, which is typically corresponding to the thrust vector, to the desired thrust vector, and thereby effectively maximizes the response for the outer loop position control loop in helicopters. Once the tilt is corrected as quickly as possible, then we correct for twist. This method has been successfully applied on quadrotors, where the tilt is also much faster than the yaw, than the twist. Twist is done with torque of propellers and is always slower. The yaw is also less important for the position control. How does tilt twist work? Well, if we represent the current attitude with a rotation matrix RC and the desired attitude with a rotation matrix RD, then the matrix multiplication with the inverse yields the error in between both. And the last column represents a vector of which the arctangents of some elements are the tilt rotation in X and Y plane. For the twist, it's a bit more fiddly. We need to create an intermediate coordinate system called RP, which represents the attitude, what the attitude will be after correcting for the tilt error. This is done using the Rodriguez rotation formula, RV, which describes the rotation of a vector along another vector. And the twist error is then defined as the inverse cosine of the dot product between the two x-axes. What does the difference between quaternion control and tilt-twist control look like on a system with slow yaw dynamics? To investigate that, we created a Simulink model in which the yaw axis was made 10 times slower than the other axis. When you start with a large error, you can see that the pitch and roll angles, in the case of quaternion control, only start to go towards 0 when the yaw angle is actually also 0. For the tilt twist control, on the other hand, the pitch and roll angles very quickly at 0.6 seconds have reached their set point. This means the tilt vector or the thrust for a quadcopter is pointing in the correct direction, and of course this is used in the outer loop for the position control. In other words, this simulation shows that with normal quaternion control, as long as your yaw angle is not reaching the desired value, then your pitch and roll are disturbed. And for some platforms that's particularly important. For instance, in the nader drone with very long wings, which can catch wind, this effect shows up very hard. But tilt twist was designed for quadcopters or all platforms in which the lift vector corresponds with the tilt vector. But tail-sitting UAV transition from hover to vertical to half transition flight, where the pitch angle changes 90 degrees. So in a pure hover without wind, the lift vector would be in the Z direction. But whenever there's a lot of wind, the total lift vector and thrust vector will be in the X axis. To address this, dynamic tilt twist was introduced, which states that not the tilt axis should be performing the shortest rotation, but the lift axis, and by introducing a rotation matrix with the transition angle, we can achieve that. The total formula for dynamic tilt twist comprises of a simple correction for the transition angle before performing the same tilt twist algorithm as shown before, and the feedback error then needs to be reconverted after having had its lower gain, so that there's time separation between tilt and twist. To address this, we made a simulator with a more complete model of the drone, the nader drone, and had it fly between 2 points back and forth. But during the flight, large jumps in set point were introduced, errors which the drone could never track, errors way beyond its capabilities. In the bottom plot, you see that the desired set point has abrupt changes to simulate what would happen in case the wind would pull on a wing or turbulence would destabilize temporarily the yaw of the nader drone, and then seeing how the rest of the position control holds up. The result looks like this. We compared quaternion control in the first plot with normal tilt twist and with dynamic tilt twist, 3 controllers. The simulation included a model that was not perfectly tuned, but nevertheless you can clearly see that the quaternion control yields much less repetitive patterns, and that the one that's most aligned with the desired direction is the dynamic tilt twist control. The exact same algorithm was then tested on the real nader drone. Here we see a takeoff. It's a so-called angled takeoff. And here's the start of the test. The first part, we have this aggressive 45-degree heading angle changes, while at the same time it's trying to precisely track a line from A to B, back and forth. Here's another aggressive yaw change, and that results in at least over a second where the drone cannot precisely follow the yaw command, and during that time it goes away from its desired set point. With tilt twist control, depending on the wind conditions, for instance, if there's no wind, tilt twist control, where the drone will be perfectly vertical and where the lift will be in the direction of the tilt, yields great results. For this test, we awaited much more wind, where you can see that the drone is at about 50 degrees nose down attitude, which already yields quite some couplings. And finally, when we enable the dynamic tilt twist, we see that the drone moves a bit more, so it compensates faster. But the final goal, the desire from the beginning, is to stay more precisely on the line and not put too much importance on the yaw, is perfectly achieved. The final phase of the flight is a manual landing. So you can see the weather was not so great, it was actually raining. And without winds, we're close to the ground. In the ground effect, the drone is almost nose up. Let's have a look at the same flight plotted in graphs. The first part is again the quaternion control. The relative wind direction is indicated with the arrow, so it had a phase where it was actually facing the wind much more and a bit flatter, and a part where it was going backward. We again see, just like in simulation, that the quaternion control has much worse position control and when it is further off the desired path, which is indicated by the red line. The tilt twist control does a lot better, and as I said, without wind, it actually does very well. But the dynamic tilt twist is closest to the desired line in this flight. Expressed in numbers, so the distance between the current instantaneous position and the desired position was an average of 3.27 meters for the quaternion control, 2.7 for the tilt twist, and 2.08 for the dynamic tilt twist. Conclusions. Quaternions give the shortest rotation between the attitude and the set point. It's a mathematical formula which is, there's no shorter rotation. But if you have very large set point errors and you have differences in response speed for the 3 axes, which is definitely the case for transitioning hybrid UAV, then it does not give the optimal solution, as the thrust factor is not doing the shortest rotation. Tilt twist, on the other hand, does give the shortest rotation of the tilt factor, but in hybrid and transitioning aircraft, this does not always align with the direction of lift, and thereby it's a great method for quadcopters and helicopters, but has shortcomings in transitioning aircraft, like the nadir drone. The dynamic tilt twist gives the shortest rotation of the lift factor, even on a transitioning UAV. To combine this powerful tilt twist ID with a powerful controller as IMV gave very interesting results. To our knowledge, this is the first time that IMV and tilt twist was combined. And the proposed dynamic tilt twist also yields the shortest rotation of the lift factor independent of the transition angle on the platform. And from flight tests, we could see that this helps in reaching the smallest position error. For precision flying and landing, this is the most important metric. Flight tests were performed on the nadir drone and yielded a clear improvement. This was our presentation of hybrid UAV attitude control using IMV and dynamic tilt twist. Thank you for your attention, and if there are any questions, we'll gladly try to address them. Welcome to the presentation of the paper called.
Okay, so thank you, Christoph, for this interesting presentation. It's very, very exciting to see this experimental test. So maybe we have time for one question. There are the question? No? Are you here, Christoph?
Yes, I'm here.
Okay, so I have one question. For example, in the case of the quaternion control, I think that you are using the vectorial part of the quaternion error. Okay, So do you use the same gains for the three components?
Thank you for the question. It's a very interesting part of the theory. So quaternion represents in body axis rotations around 3 axes, and when you can react at the same rate around all axes, then there's no problem. But in a lot of platforms, the actuators have different response speeds and also sometimes even different deflections. So that means that if the actuator is different, then you will also have another gain. What some people have done is to choose the gains in such a way that the turn rate in all 3 axes becomes similar, which actually can only mean one thing, is that you slow down the faster to match the slowest. And that is, in terms of position control, also not very elegant, because the platform could be faster. I hope this addresses your question.
Okay. Yeah, because maybe if you can use different gain in each component of the quaternion error, or even you can use the saturation function. Maybe you can regulate the speed of convergence of H8. So, but maybe, maybe it's only a suggestion.
Yes, you can definitely do that. You can make it react along the desired rotation that the quaternion describes. And the solution to do that is to slow down the fastest axis to the speed of the slowest, so that then you can guarantee that the rotation is along the desired axis. So we do use different gains on all axes, but chose an approach which maximizes the use of the fast responses in order to get better position.
Yeah. Okay, I agree. Okay, so thank you very much for your response. Thank you for your presentation. Okay, so we continue. The next paper is the paper number 7. Are you here? The author of paper number 7 is here.
Yeah, here.
Ivan, okay, Ivan Martinez.
Yeah.
Okay, Ivan, so you have 15 minutes for present your work.
Right, yeah. Can you see the presentation?
Yes, we can see.
Okay, so well, hello everyone, welcome to the 12th International Micro Vehicle Conference and Competition. My name is Ivan Martinez Perez, and then I'm going to present the article called Slide Mode-Based Through Vector Control for Aircrafts. Part of the contents of this presentation, we have a brief introduction, followed by the rocket dynamic model, made up of translational dynamics, rotational and translational kinematics, and finally the proposed control design and conclusions. In recent years, the research to achieve reusable spaceflight has been a very active area. So we focus our attention on propulsion systems that include thrust vector control, TVC, which allow us to change the flight path to follow a desired path. In this article, we propose an attitude about the experimental rockets using TVC, where the equation of pitch attitude and inertial z-axis trip position are obtained. Basically, 2D. So assuming that some parameters of the aircraft are known and the airspeed is uncertain, we make it our goal to guarantee the convergence of the pitch angle and the drift position using a sliding mode based thrust vector control. Finally, some simulation results are present to show the performance of the proposed controller under different conditions. The main assumption to carry out this work was that the rocket is considered rigid, without flexibility, constant mass, with approximate aerodynamic coefficients, and considering only a single engine and therefore a single nozzle for control. The geometry of the air is considered as the ellipsoid proposed by the World Geodesic System in 1984. The position of the rocket is defined by the Earth Central Inertial Reference Frame, while the orientation is defined by the reference frame of the body, or rocket frame. Well, starting with the modeling of the rocket dynamics, we have that is defined firstly by the translational dynamics to obtain the position of the rocket at each instant of time, which is defined from Newton's second law, where it's necessary to know all the forces acting on the rocket, which are thrust force, aerodynamic force, made of lift and drag, and finally the gravity force. Thus, we obtained the equation 2.5. Well, so defining each of these forces, we have the first of them, the thrust force. As we see in equation 2.2, where is the represents the total thrust force. As well as we see in figure 2, taking only the components by means of triangle relationships, we obtain the thrust vector control. In figure 3, we observe the angles delta theta and delta psi that represents the 2 degrees of freedom of movement of our nozzle. Finally, we obtain the equation 2.3. Now moving on to aerodynamic forces, we have the lift and drag, where for simple geometries, as the rocket, we can use the component of the normal force M, as we see in figure 4, and the axial force A. Now changing plane, in figure 5, we can see the third of them, the lateral slip force, which in figure 4 will normal to the plane. And thus we obtain equation 2.4. Now for more real condition, we know that the rocket in flight tends to have a small deviation known as track, where the angle formed by it and the actual trajectory is known as drift. So as we see in figure 6, the vector B represents the track, and the angle formed by it and the z-axis is the angle of drift by gamma, the letter gamma. So we have this same peculiarity in the figure 7. So defining each of these angle, the angle of attack as alpha, and the angle of lateral slip beta. Firstly, we have the orientation angle, the drift angle, and finally the angle of the air disturbances. So redefining the last equation, the equation of the aerodynamic forces, by S and N about the forces, we obtain the equation 2.7. Well, now as the last force, we have the force of gravity, whereby using the ellipse of WGS 84 for a better approximation of the geometry of the air, a better approximation of gravity is obtained. It should be noted that this model is by the geocentric inertial coordinates, so it is necessary to make a transformation. Thus, we obtain equation 2.8 about the gravity force. Finally, the translational dynamics, considering the aerodynamic force in conjunction with the disturbance, the thrust force defined by the thrust vector control, and finally the force of gravity, considering the geometry of the air as the ellipsoid WGS 84, we have as result equation 2.9. So now, to obtain the rotation of the rocket, the rotational kinematic is defined, which are easily applied in aircrafts. We made use of the Euler angles, yaw, pitch, and rho. Then, this rotational kinematics with respect to the SE frame, reference frame, is described as in equation 2.10, which depends on the angular velocity. Now, to obtain the rotational dynamics from Euler's second law for a rigid solid in rotation, it tells us that the sum of moments is equal to the derivative of the angular momentum, where in turn this is equal to the moment of inertia times the angular velocity. Then we obtain the equation 2.11, where it's necessary to define the rocket moments, which are the aerodynamic moment and the thrust moment, as we see in equation 2.12. And the aerodynamic moment is defined by the distance from center of gravity to the center of pressure times this force, as in equation 2.13. And the moment of thrust is defined by the distance from the center of gravity to the engine gimbal joint, as in equation 2.14. Finally, we define equation 2.15 that describes the principal moments of the rocket, where finally, by substituting this equation, we obtain the equation 2.16. Well, as a result, we have that the rocket dynamic model has 9 degrees of freedom according to the dynamic equation that are needed to define it, with 2 being the maximum order of the rocket, of the system. Sorry. Finally, the main difference between this model and the others is the consideration of the TBC for a single nozzle and the aerodynamic disturbance. Now, starting from the mathematical model developed, assuming that the depth in the y-axis doesn't exist and taking only the xc plane and not considering the movement in x, we have that the angle phi and c are 0, as well as the angle and lateral elliptic force. In addition, that the delta epsilon nozzle angle are given by the thrust vector control. Likewise, the CY and XY planes and their combination don't exist. And finally, considering that the rocket performance angles and the TBC are small, we say that the cosine of the angle is equal to 1 and the sine of the angle is equal to the same angle. In this way, we obtain as a result the system with movement in 2D as in equation 3.1 and 3.2. Returning to the previous model and writing it as in equation 3.3, where fx represents the matrix of the system, gx the control vector, x represents the state of the system, where c and c dot represent the height, and theta dot represent the orientation. Finally, the control input is delta theta with respect to the thrust vector control. The control law is then proposed as defined in equation 3.4, where the surface S1 is defined as x1 plus x4, and G2 and KD as feedback gains. Now, taking the following proposition, considering the law of the previous equation 3.4, to control the flight path, height, and pitch angle in a rocket, then the convergence to the origin is assured infinite time if KD is large enough for any practical conditions. Then, by means of a stability proof, we aim to check the condition of the sliding mode, that is that the surface tends to 0, choosing a sufficiently large gain. This implies that according to the theory of sliding modes, it is possible convergence infinite time to the surface S from an initial condition. Then, when S is equal to 0, the trivial solution is that x1 and x4 are equal to 0. That is, z and theta dot tend to 0. This considering physical that the rocket is in initial condition far from the origin in flight, and we want to land or reach a desired point. The following table shows the parameters for the numerical simulations. And now we can see the results where the simulation objective is that C and theta tend to the origin given an initial condition. As we see in figure 10a, the control is able to bring it to the origin as the desired state. And in figure 10b, the control stabilizes, and finally the angle of drift and the angle of attack in the remaining figures also tend to the origin. Now, starting from this same simulation, adding the aerodynamic disturbance, we have two cases with the intention of checking the robustness of the controller considering their parametric functions. Then in the first case, we have the disturbance is considered a sinusoidal function, where its behavior is shown in figure 11a. However, despite this noise, the control is robust enough to bring the rocket to the desired state. In the second case, being more rigorous, we propose the disturbance as a Gaussian function, as we see in figure 12a. It is of higher frequency, and as expected, the controller complies with the desired robustness. Finally, as a piecework bonus to this presentation, a preliminary experimental result on the rocket is presented in order to control an experimental rocket by TVC as a part of my master thesis in aerospace engineering in Universidad Politécnica Metropolitana de Hidalgo, México. The experimental rocket is characterized by having two angles of freedom with a servo for each one, and the propulsion is carried out by means of compressor pump. In figure 12, the horizontal movement is shown, while in figure 13, the vertical movement. Finally, the figure 4 shows the stabilization test. Well, so the conclusions of this work are the following. A complete dynamic model of the experimental rocket using a TVC is presented. The angle of attack control, which allows to reduce the drift in flight through TVC, is proposed using a reduced dynamic of the rocket today. A reduced dynamic of the rocket is proposed to control the angle of attack, which allows us to reduce the drift in flight through TVC. And finally, a model-free sliding mode-based TVC is presented to guarantee robustness in the presence of parametric uncertainties. So this is the main reference to this work, and thank you for your attention.
Okay, thank you, Ivan, for this exciting presentation and for this exciting work. I see that there are many theoretical aspects here. We have time for one question. Are there questions of the audience? We can set me question here in the chat if you want. Okay, in the meantime, Ivan, the classical question is, why do you choose the slide mode control for your work?
Can you repeat it again, please?
Why do you choose the slide mode control for this work? Why not PD control or another approach?
Yeah. Well, we are focusing on the air disturbances. We realize some other proofs about other controls, like you you said, PD or the linear quadratic regulator, some like that. Well, we couldn't control the system. So technically, it's about the response that we obtain. So in this particular work, we can we can control the system only with this backstating slide mode controller. So that's the reason.
Okay, I think also the reject of disturbance is an objective in your work, no?
Yeah.
So I think the slide mode control has many beneficial contribution in order to reject the disturbance. So maybe this is the main reason. Okay, so thank you, Ivan, for this presentation.
Yeah.
Okay, so we continue. The last paper is quaternion-based attitude slide mode control with disturbance rejection observer for unquad rotor. And the paper is the number 17. So the presenter for paper 17 is here. Juan?
Yes.
Okay. Okay, so please, Juan.
Okay, I will share the presentation.
I can see your presentation. Juan,
Sí. Yes.
You can send video, no?
Yeah, it's a video.
The volume is very slow.
Oh, okay. I will.
It's very low. Maybe.
Okay. I don't know. Okay, I will present the presentation live to avoid this problem. So
If not, we can put we can play the video. Okay, so maybe Oyuki, you can play the video, Oyuki, please, because it's necessary to perform any tricks for that, I think.
okay, I continue with the video or
no? Wait a minute, please.
Okay.
You can stop sharing your screen. We are going to play your video.
Repeat, please.
Could you stop sharing your screen?
Okay, yeah.
So, because we are going to play your video, no worries. So Oyuki, please.
Okay.
When you are ready.
Yeah.
And then at the end of the video, we can have the questions and you can answer. Okay, there we go.
Okay, thank you.
There is no sound, Oyuki?
The video was recording with a very low sound.
Is there any sound with the video, Oyuki? Or can you fast forward to see whether there is any audio?
Yeah, it's only the audio. So I
No, it's only the video, no? There is no audio?
no. Yes, they have audio, but it's very slowly,
Very low.
very low. Sorry.
Mhm.
So continue the video or stop the sharing.
Oh, Juan, you can present in live?
Yes.
Okay, so we can switch.
Yeah, let's go for it, please.
Yeah. Okay. Um, 1 minute, please.
No words.
Okay, can you see the presentation?
Yes, yes, we can see.
Okay, I will start. Sorry by the issues. Yes. Okay. Okay. Our work is called quaternion-based aptitude sliding mode control with a disturbance rejection observer for a quadrature. And we are Juan Ayala, Rogerio Enriquez, and Fermi Guerrero. The content of this presentation is as follows. First, I will give you an introduction. Then I will talk about the objectives of this work, followed by the methodology. Then I will show you the results. And finally, I will give you the conclusions. So the quadratures are unmanned aerial vehicles used for multiple applications like filming, farming, vigilance, light shows, or transportation. These tasks expose the vehicles to multiple. Sorry, I have a problem. One moment, please. Okay, sorry about that. Can continue?
Yes, but we can see your screen.
Okay, I will share now.
Okay.
Okay, so I was saying that the vehicles performing this task are exposed to multiple perturbations like wind gusts or environmental problems coming from other vehicles or walls. So to perform this task, a control is needed, and this is divided in 3 controllers, like the guidance controllers, where the trajectory is defined, the position controller, where the position is achieved to follow the trajectory, and the attitude controller, where the rotations of the vehicles are performed. This directly affects the position controller because the underrotated nature of this system. In this work, we focus on the attitude controller. For the attitude of the rigid body, there are multiple representations like Euler angles, axis and angle, unitary quaternions, Rodriguez parameters, or direct cosine matrices. The unit quaternions has some advantages, like there are no singularities and only have one constraint. Also, there are a good option for faster calculations and more accurate. So the quaternions are hypercomplex numbers formed of 4 elements grouped in a scalar and a vector part. For the representation of a rotation, a unitary quaternion is needed and can be transformed to the Euler angle using this formula. Also, a quaternion can be used as a rotation operator using the quaternion product operation. A logarithm of a quaternion allows to represent the rotation in an axis and angle form using this transformation. And by the derivative, of this result we can obtain the angular velocity. The quaternion-based model of the quadrator is writing in this form, where the C is the vehicle position, the Q is the attitude quaternion, omega is the angular velocity, K is the inertia matrix, and tau is the control torque. By applying the logarithm mapping, the quaternion model is written in this form, and we can obtain the angular velocity directly from the quaternion. In the literature, there are multiple control techniques applying in quadrators. They're ranging from linear controllers, non-linear controllers, to learning-based controllers. In our work, we are focused on the sliding mode control, which is a technique where the idea is to attract the system to the state toward a surface called the sliding surface. Suitably chosen and design a stability control law that gives the system states on such surface. The main advantages of this technique are its fast response and good transient performance. Also, its robustness against a large class of perturbation and uncertainties. And its major disadvantages is the chattering due to high frequency switching, and this can lose on energy and a model dynamic and even actuator destruction. The sliding mode control has this general form for the first order, and the control law is formed of two terms. First one is equivalent to the system, and the second one is non-linear, depends of the sign of the surface. The objectives of this work are design a control law based on a slide mode technique for a quadrator using a quaternion-based model, and design a steady state observer to improve the rejection of external perturbation and uncertainties in the model. The sliding mode control applied to the quadrator is shown in this block diagram, where first the position control receives the reference position, where the total force is obtained, and the desired angular velocity and desired quaternion are the inputs to the control, the attitude control, where the control torques are obtained, and the outputs of the system are feedback. Also, we apply some disturbances to the input control of the system and the inertia matrix to check the robustness of the control. The position control is designed from the position subsystem of the model and can write in this form, so can be treated like a linear system, and this control law is proposed. it's where she had is a position error. And from the error dynamics, we can obtain that the constants K1 and K2 must be greater than 0 to the error converge to 0 as the time tends to infinity. The design of the attitude control is from the rotational subsystem using the logarithm mapping and defining the error quaternion, like the difference between the desired quaternion and the quaternion of the system. The desired quaternion is obtained applying some properties from the quaternion product and the logarithm and exponential operation. So choosing a sliding surface of first order where omega e is the angular velocity error, from the derivative of the sliding surface, we can obtain the control law for the attitude of the quadrator. The appliance.
5 minutes. One, please.
Okay. For the observer, we can we choose to apply it to the attitude control to minimize the effects of the perturbation in this way, as it shows in this figure. So the aim of the observer is to estimate the angular velocity and the unknown disturbance d. This is because the angular velocity depends directly from the uncertainties in the inertia matrix. So defining the observer in this way, where x1 hat is the angular velocity and x hat 2 is the disturbance. I will show you the simulation results in this section. So for the simulation, we choose these parameters and these design control constants. And for the trajectory of the quadrator is an upward spiral where the quadrator is following smoothly and with small errors. So in the same way, for the attitude control result, we see that after a brief transient of about 3 seconds, the error in the orientation is very low. So comparing the results from the sliding mode control only and with the observers, we can see that with the observer, the error is smaller, up to 10 times. The disturbances are just uniform noise added to the inertia matrix, about 20% of the nominal value, and as an external disturbances is a sine function added to the control torques. So using the is an index, we can see that the results with the observer are 3 orders of magnitude smaller than without the. Well, for conclusions, we have nonlinear sliding mode control proposed for the attitude stabilization and tracking of a quadrature vehicle, and an extended state observer was designed to estimate the model uncertainties and improve the unknown rejection and non-disturbance rejections. Finally, the results show that the observer improves the disturbance rejection up to 10 times. That's all. Thank you.
Juan, thank you very much for this presentation. Maybe we have time for one question. Is there a question? No. So only for curiosity, what is the advantage with respect the quaternion with respect to Euler angles, Juan?
Well, as we see in the presentation, the model is simplified. Also, some singularities are avoided, and we can say the calculations are faster because of the avoid of the matrix operations and the approximation of sine and cosine functions.
Okay. Okay, so thank you very much, and thank you for your attention at this session. This was the control system session. So thank you very much. And maybe Jose has some message for the audience.
Yes, thank you, Fermi. Thank you very much to the speakers of this last session. We are at the end of the day for this second day in the IMAV 2021. So I just want to invite our audience to join us tomorrow. Tomorrow we will have 2 other excellent keynote presentations. Let me share my screen to show you who they are. Okay, so tomorrow in the morning at 9 a.m., we will have Nicolas Marchand, Deputy Director of GIPSA Lab, and this lab is located in Grenoble, France. So I'm pretty sure it's going to be a very nice talk. The keynote is entitled Controlling UAVs Based on Events, a New Approach for New Solutions. So please join us tomorrow. As before, we will transmit this keynote, and in fact, all the talks are being transmitted via Facebook and YouTube. And then in the afternoon, we will have the last but not least keynote presentation that is going to be delivered by Rogelio Lozano. Rogelio is CNRS Research Director from the University de Technologie de Compiègne. I apologize for my French, it's not very good, in Compiègne, France. His keynote is entitled Stabilization and Nonlinear Control for a Helicopter with Virtual Swash Plate in Outdoor Flight. And that one is going to be at 5 o'clock in the afternoon, 17 hours, tomorrow, Friday. So please join us, come to the keynote. And of course, we will have other 3 paper sessions, the Design 1 session, Design 2 session from 10 to 11 and 11 to 12, respectively. And the last session after the keynote is going to be autonomous navigation 2. At midday, after the morning sessions, we will have the awards ceremony at 12 p.m. So please do not miss that session where we are going to announce who are the winners of the 3 prizes that we are going to award: the best conference paper, the best technical application paper, and the best student paper. And we are going to mention as well the runners-up to this best conference paper, which I also think they were very, very nice work. It was very difficult to choose which paper had to be given the best conference paper, but well, we will do the announcement tomorrow. And after the whole day is over, with all the sessions, we will have the closing ceremony. That one is scheduled at 7 p.m., where hopefully we will make some interesting announcements for what's going to happen next year. And by the way, for the awards ceremony, we will have a small surprise to the winners, and that is related to Luxonics, the company behind the OAK-D sensor, which also we had today a keynote presentation delivered by the CEO of Luxonics. A very nice presentation, and I think he made a very good case of how to use this technology with drone. So please come tomorrow, join us, and see what this is going to be about. Okay, having said that, thank you to everybody, and we can say that it is over for this day. See you tomorrow. Bye.